Okay, so what we're going to be working on now is exponential growth and decay problems. So I hear from you guys a lot. How do we use this in real life? Here's one application of exponential functions in real life, in exponential growth and decay. So I'm going to read you a little intro, but you don't have to write it all down, okay? So many real-world phenomena can be modeled by functions that describe how things grow or decay as time passes, like in chemistry, right? Examples of such phenomena include the studies of populations, bacteria, radioactive substances, electricity, and temperatures. So all of these things follow certain patterns that we call exponential growth or decay. So scientists, meteorologists, people that study sociology, people that study populations, they use these types of functions to look at the trends in populations, in bacteria growth, in temperatures, and all of that. So here's what I want you guys to write down. Any quantity that grows or decays by a fixed percentage at regular intervals is said to possess exponential growth or exponential decay. So I want you to write that second sentence, okay? Here are two examples. If your graph is decreasing, so it's getting smaller as we go to the right, it is called exponential decay. That should make sense, right? Your population is dying. Your bacteria is dying, okay? So it's getting less and less, so we are decaying. Exponential growth is an increasing exponential function because as we move on, it's getting bigger. So your population is increasing. Your bacteria is doubling every minute or something. That's called exponential growth. Definition, and then we'll get started on problems. So one definition you're going to need, which actually should be familiar to you, is called half-life. Half-life is the time required for a substance to decay and fall to 1/2 of its initial value. Radioisotopes of different elements have different half-lives. So a half-life is however much time it would take for any substance to become half of what it started with, okay? Okay, so when a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of 5,730 years. So I want you to write down that the half-life is 5,730 years. I want to know how much of a 10 milligram sample, so that's what we're starting with, is 10 milligrams, will remain after a time span of 22,920 years. Here is the formula. So N equals N sub 0 times 1/2 to the power of T over H, and then I tell you what everything means. N sub 0 is the initial amount. N equals the amount remaining, so what you end up with. T is the time in years, and H is your half-life. So write down your different values. Write down the actual equation or the formula, and write down what everything means so that you know what you're plugging in. Okay? All right, so let's plug everything that we know in. N is the amount remaining, so that's how much we end up with at the very, very end. So we don't know what N is. That's what we're trying to figure out. N sub 0 is the initial amount. How much should we start out with? What did I tell you we started out with? 10 milligrams. So you're going to plug in 10 times 1/2 to the power of T over H. T is the time in years. So the time is 22,920 over the H, which is the half-life, which we know is 5,730. So that's to the power of. Now, I'm going to be nice, and I'm going to tell you that all of this reduces to 4. So this would be 10 equals, N equals 10 times 1/2 to the power of 4. Okay, that's what it all reduces down to. Okay. So that's going to be 10 times 2 to the power of 1/4. We're going to take that exponent of 4 and distribute it on top. So 1 to the 4th gives me 1, and 2 to the 4th gives me 16. So this is going to be 10 times 1 over 16. Now because this is a 10 over 1, that's actually the same as 10 over 16, which reduces to 5/8. So 5/8 of a milligram is what is left over after 22,920 years. So I give you the information, I give you the formula, all you have to do is plug it all in. Okay? On your homework, if you get giant numbers like this, go ahead and use a calculator. On the test, I don't give you giant numbers like that, so don't freak out, okay? So I'm going to have you guys, I'm going to skip number 2. I'm going to have you guys on your own do number 3, which is almost identical to number 1. So, number 3, the radioactive gas radon has a half-life of approximately 3.5 days. Now, that's going to be killer to plug in. How else could we write 3.5 days? 3.5. About how much of a 300-gram sample will remain after 1 week? And then I gave you a hint. Remember to convert 1 week to days. Why would we have to convert 1 week to days? Yeah, our half-life is given to us in days, and our amount of time is given to us in weeks. They have to be the same unit. So 1 week is how many days? 7 days. So you have to keep your units the same. So make sure you convert if you have to. So we have a half-life of 3.5 days and a time of 7 days. So plug everything into the formula that I gave you using the information given. And then I'll check in with you guys in a minute. Let's do this together. Okay, guys, did you plug anything in for y? No. So this should be y equals. What did you plug in for a? 300 times 1/2. What did you plug in for t? 7. And what did you plug in for h? 3.5. Good. Okay, now we have to take care of this exponent first. 7 over 3.5 reduces to what? How many times does 3.5 go into 7? Twice. So it actually reduces to 2. So that's going to be y equals 300 times, what's 1/2 to the second power? 1/4. So this is the same as 300 divided by 4, which should be pretty straightforward. How many times does 4 go into 300? 75. But we're measuring how much of a sample, so we're going to be measuring in grams. So after a week or 7 days from our original starting of 300 grams, we end up with 75. Okay? Okay, this time we're growing. So number 6, a culture of yeast doubles in size every 20 minutes. The size of the culture is now 80. So we're starting with 80. Find its size in 1 hour. And then it tells you, remember, to convert your hour to minutes because it tells us that it's doubling every 20 minutes. So we have to keep everything in minutes. How many minutes is 1 hour? 60. So it's actually going to be 60 minutes. Okay. Okay, so let's plug everything in. Do we plug anything in for y? No. What's our initial population? What are we starting with? What does it say that the size of the culture is when we start measuring? 80. So that's going to be 80 times 2 to the t over 20. How much time are we measuring? 60 minutes over 20. Where do you think they got 20 from? How often it doubles. They just give it to you, which is nice of them. Okay, so let's reduce. 60 over 20 reduces to what? 3. So this is going to be y equals 80 times 2 to the third power. So that's y equals 80 times, what's 2 to the third? 8. So 80 times 8 gives us 640. And the way that they measured was just in the number, so we don't have to put any units. So the size after only 1 hour is 640. So that's growing really fast because we started with 80. Okay? But it's doubling every 20 minutes, so you should expect that it's growing really fast. Okay? Okay, so you guys are going to do this one on your own. The growth of a town is given by this formula. Y equals y sub 0 times 2 to the power of t. Y sub 0 is the initial population, t is the time in years, and then they give you your information. If there are 4,000 people after 4 years, find the initial population. So I'll actually start this one with you. Do we plug anything in for y in this case? Well, let's think about it. Do we know what the initial population is? No, that's what we're asked to solve for, right? But they tell us that there's 4,000 people after a measured amount of time. So where are we going to plug 4,000 in for y? This is going to be 4,000 equals y sub 0, we don't know what it is yet, times 2 to the power of 4. Okay, finish it. Okay, guys. So this is going to be 4,000 equals, oh, I don't know why I put a comma there. Y sub 0 times, what's 2 to the 4th? 16. Okay, so we have y sub 0 times 16. How would I get y sub 0 by itself? Divide by 16. Okay, I'll do the math for you. 4,000 divided by 16, good, comes out to 250. So y sub 0 comes out to 250, what? People. So it was a really, really, really small town, and now they have 4,000 people. So it's still a really small town, but not as small, okay? Okay, so the number of people with a flu virus is growing exponentially with time as shown in this table. So on day 0, the first day that we start recording, we have 300 people with the virus. The following day, so 1 day has passed, we have 600, and the day after that, we have 1,200 people with the virus. So what we need to look at is we need to determine what the equation is for the exponential growth of this virus. Okay, so did you guys see any similarities between the two graphs from before? Yeah, it's always going to be the amount you end up with equals the amount that you start with, so y sub 0, times either 2 or 1/2. It just depends. If you guys notice, what's happening every single time, every day? It's doubling, right? So if we are growing exponentially by doubling, your base of the exponent is going to be 2. If it's a decay problem, the base of your exponent is going to be 1/2 because it has a half-life. Okay, so it just depends on what kind of problem this is. Because this is a growth problem and we are doubling each time, you multiply your initial times the amount that it's growing, so 2, and your exponent is always going to be the amount of time, always. So you actually could be given a chart that looks like this and write out your function every single time using this basic formula. So, looking at that, we have y equals y sub 0. That's your initial population. What was our initial population that has the flu? 300. Times 2. Do we know how much time has passed yet, technically?
2 days.
Well, we can't just put 2 days because they're still measuring it. So we would put t. Okay? So look at your multiple choice answers that I give you. Which one looks like it's written in this format? 300 times 2 to the t. t. The variables are just different, but it's the same. Okay? So you will be asked to do something like this as well. So just make sure that you know what the basic formula looks like, and we'll continue practicing, and so that you can write it out. But it's always going to be your initial times by how much you are growing, so doubling, tripling, whatever, to the power of 2. Okay?